right. Hi, everyone. I'm super excited to be here in Stockholm for the Data Innovation Summit. And thank you all for joining us today. I actually want to start by really giving a huge round of applause to the Data Innovation Summit team for organizing such an amazing event. So let's give it to them. Oh, thanks. All right, so my name is Hagay Lupesko. I'm an engineering director at Meta, and I work on AI and machine learning. And today I'm going to talk to you about foundation models, which is an exciting emerging paradigm in AI that offers both opportunities and challenges for implementing AI in the enterprise. Before we get started, actually, with a show of hands, I'd like to kind of know a bit better about what you guys are doing. So who has been working on implementing machine learning systems within their company? Raise your hand. If you've been involved in machine learning systems setup, great. Okay, so quite a few. How many of you have been working on deep learning systems? With a show of hands. All right. So quite a few as well. So you're going to find this talk fairly interesting, I hope. Let's jump in. So first, we'll take a step back in time and look at the rapid and somewhat surprising rise of deep learning less than actually a decade ago. And you might ask why the rise of deep learning is surprising. Well, today, it might be hard to believe, but until just a decade ago, most professionals in the AI field consider deep learning to be irrelevant because of challenges of scale and learning instability. But actually, if you look at this graph that shows the deep learning search term popularity, you'll see that until roughly 2012, 2013, that term was not popular at all. And since 2013, there was a huge uptick that peaked around 2019 and stayed fairly popular ever since. What happened then in 2012? What happened was that AlexNet, a deep learning model for image understanding, was published and made a huge breakthrough in terms of being able to understand images. So the AlexNet research team was a brilliant team coming out of the University of Toronto, and they made a huge achievement with AlexNet. However, there were a few key trends at the time that enabled them to make AlexNet such a huge success. First of all, there were massive labeled data sets that became available at the time, thanks to the fact that everyone started working with a camera in their pocket, their smartphone, and thanks to the rapid rise of the internet that made all of that content that people created and collected publicly available. ImageNet is an image data set with 14 million labeled images and around 10,000 classes of labeled data on those images that is publicly available. And what made deep learning training possible with this data. Second, GPUs became available for not just for gaming. So GPUs were designed originally to enable 3D rendering of computer games. But what happened is that general purpose APIs for GPUs became available, and the AlexNet team programmed against these APIs and were able to train AlexNet on just 2 GPUs, making it possible to train it, because before that, on CPUs, training deep learning models was just impractical. It would just take too long. And last but not least, the algorithmic backbone for deep neural network reached a critical stage where training became stable. So things we take for granted today, such as layer normalization, dropout, ReLU activation, these are all things we take for granted today when we build deep learning models, but at the time they were novel, and the AlexNet team used all of them together in building and training AlexNet. Now, these 3 factors combined basically enabled the AlexNet model to win the 2012 ImageNet Challenge by a huge margin. It was 10% difference from the second best model in that competition. And what's interesting is that until 2012, no other deep learning model won that competition. But from 2012 onwards, every winner of the ImageNet challenge was a deep learning model. So with this big success, both academia and industry took notice. And what we've seen since then, is that private investments in AI started upticking significantly. If you look at 2013, overall investment in AI was just under $3 billion a year. And if you fast forward to today, AI investments are over $90 billion annually and still growing. So there are many researchers that have made important contributions to the emergence of deep learning, but it's worthwhile to note three leading researchers from that community. So Jan LeCun, Jeffrey Hinton, and Yoshua Bengio. Three of them are now considered AI luminaries, and in 2019 they were recognized with the Turing Award, which is the highest recognition for computer science researchers. So today, deep learning is really everywhere. The pace of advances of both research and application of deep learning has been mind-boggling. Deep learning works, and it works big time, and is today powering our day-to-day lives in lots of different ways. If you look at super precise personalization algorithms that are running on social media sites, on your favorite streaming service, for video or audio or e-commerce, if you look at natural sounding know-it-all voice assistants that were made possible thanks to deep learning, and up to up-and-coming things like autonomous vehicles or drug discovery with deep learning. All of these things are made possible with deep learning. But the state-of-the-art deep learning is actually hard. If you've ever tried to apply deep learning in your own systems, you know that it's hard. And why is it hard, really? There are a few key reasons. The first one is data. And as we all know, machine learning and deep learning is mostly about the data that you have, both the quantity of the data, but just as important, the quality itself. Deep learning requires a lot of high-quality data for the model to train properly and to work properly and deliver results and avoid overfitting. Now, the problem with that is that curating large-scale data sets is actually very expensive, it's very time-consuming, and it's very costly. Then there's the increase in model scale and model complexity. If we look at AlexNet, which we just spoke about, it was a state-of-the-art model for image understanding back at just 9 years ago, and it had about 60 million parameters. It took about 5 days to train on 2 GPUs. You fast forward to today, 9 years later, there is a new state-of-the-art image classification model called Florence coming out of Microsoft. It has close to 1 billion parameters. So we're talking about 20x growth in the number of parameters. If you look at the time and resources it takes to train Florence, it requires about 10 days on 512 NVIDIA A100 GPUs. So model sizes grew 20x, training resources and time is increased by 500x. And as we can see, state-of-the-art models today are growing very large and take much, much more time, compute, and also money to train. And last but not least, talent. That's basically all of you guys here. Advanced neural network became very complex, and developing, training them, and serving them requires high level of expertise across lots of different domains, from data engineering through modeling up to system infrastructure. And since the population of software developers and machine learning developers didn't scale as fast as deep learning, we're now at a position where there is a real war for talent going on. It's pushing up both the cost to hire people as well as the time for hiring professionals. So all of this adds up to basically making advanced deep learning application hard, time-consuming, and costly. So far we've briefly discussed the journey deep learning made over the past decade, the success of AlexNet, the rapid progress and enormous value delivered. And now I'd like to introduce you to a relatively new concept, a new paradigm, one that may be the next chapter in the path of deep learning and AI, and one that might make application of deep learning in the enterprise much more accessible and feasible. This new paradigm is called foundation models. Late last year, in August 2021, a group of about 100 researchers from Stanford published a technical report where they coined a new term, foundation models. That report came out of a new center in Stanford, the Center for Research on Foundation Models, the CRFM, and it's dedicated to just focusing on foundation models. That report is about 200 pages long, so it's fairly long, and it reviews many aspects of foundation models across science, engineering, as well as society. Now, we're not going to dive into the report in this session, but I did want to share a quote that tells the big story in short. AI is undergoing a paradigm shift with the rise of models that are trained on broad data at scale and that are adaptable to a wide range of downstream tasks. We call these models foundation models to underscore their critically central yet incomplete character. So that quote, that definition says a lot, but example for such models can be BERT, that was mentioned earlier, GPT-3, which I'm sure you all heard about, as well as vision transformers, or VIT for short. Now I'd like to try and unpack the definition of foundation models to make it a bit more concrete and try to understand why this is really a paradigm shift. All right, so there's really three main properties of foundation models, and we'll start with the first one, architected for high capacity. So architecting for high capacity is what enables the foundation models to learn general and high-level representation of content, such as text or images, and it's learned from really massive data sets. Now, to design such high capacity, foundation model architectures need to leverage deep networks with tens or sometimes even hundreds of layers, as well as leveraging advanced modeling techniques. The most recent one is transformers. This results in very high parameter count and computational complexity for both training and inference. And this table that we've compiled here shows just how much model sizes have been trending and growing for state-of-the-art language models over the past just 4 years. And you can see BERT with 340 million parameters, then GPT-3 with 175 billion parameters, and most recently PaLM coming out of Google with 540 billion parameters. And mind you, on this graph, the y-axis is logarithmic scale, making it clear that what we're looking at here is exponential growth in model sizes. Model sizes grow by about an order of magnitude every year. And what's even more interesting is that this trend is not showing any signs of slowing down. That's truly phenomenal. Second part of the properties of foundation model is that they're pre-trained on broad data. Let's understand that. So huge data sets, typically scraped from across the internet, that's what powers training of foundation models, or as it's called, pre-training. And while vision training data typically requires labeling, language models, their training is usually done with self-supervision. So they don't even require labeling, what makes scaling these data sets to be larger and larger relatively easier. Now, ImageNet that we spoke about earlier, it's a well-known vision data set consisting of 14 million labeled images that are labeled across 21,000 classes. Common Crawl is a language data set, and it's built by regularly scraping the internet and publishing the scraped data on AWS so anyone can access it. If you look at January of this year, Common Crawl is about 320 terabytes of data used for training foundation models, and it's scraped across about 3 billion web pages. And there are many other data sets. Some of them are closed and even larger. As an example, Google has JFT3B. It's an image data set with over 3 billion labeled images. That's phenomenal. Lastly, and that's actually the most important attribute of foundation models, is their capacity to be adaptable for downstream tasks. And that's where the value comes for foundation models. Now, considering foundation language model, they can be adapted to handle many classical NLP tasks, such as question answering, translation, or sentiment analysis. And in fact, models like BERT or GPT-3 show state-of-the-art results when they are adapted for these downstream tasks. So I'll repeat that part. You take a foundation model that was trained for general tasks, you adapt it, and you get state-of-the-art results, meaning the best results across models, including models that were trained specifically for that downstream task. Similarly, for computer vision, foundation model for computer vision can be adapted for image classification, object detection, deepfake detection, and just like language model, foundation model for computer vision, such as Florence, published by Microsoft, shows state-of-the-art results on many computer vision tasks. I'd like to stop and dive deeper into adapting a foundation model, because this is really the power and value of foundation models. And as of today, there are really 3 main ways in which foundation models can be adapted. Let's go over them. The first one is fine-tuning. Now, to fine-tune a foundation model, you load the pre-trained model with its weights. You usually add a layer on top, such as a linear layer with softmax for the task at hand, and then you train that new model you've created with the task-specific data set that you have, and you typically backpropagate throughout the entire network to tune in the parameters, the weights, for this specific task. Now, the great thing here is that typically with just a few epochs of training, you are able to get state-of-the-art results. And for example, the BERT paper published by Google at 2018 actually surveys different ways to fine-tune BERT and recommends between 2 and 4 epochs to get the best results on your downstream task. Now, 2 to 4 epochs is something that on modern GPU should take you maybe 10 minutes, maybe 20 minutes. So imagine that. Within 10 to 20 minutes of training, you're able to get state-of-the-art results. The second method that can be applied to adapt foundation model is embeddings. And here we use the foundation model as really a feature encoder that takes in the content the model is trained on, such as a sentence in natural text, or maybe an image, or maybe a video. And the model computes an embedding, a dense vector out of this input. And that dense vector is extremely useful because it's very information rich. And it can be used in downstream machine learning models, both neural network or random forests or other similar models. Or you can use it as a vector for similarity search application for things like retrieval. Extremely useful method and very easy to apply. And lastly, and really that's one of the most interesting ways, is what's called in-context learning. And this is where the magic of state-of-the-art deep learning really, really shines. So with in-context learning, which is sometimes referred to as zero-shot or single-shot or few-shot learning, the model is actually able to learn the task without ever being explicitly trained for it. And what we do in this method is we provide the task as a natural text as part of the model input. We tell the model what is the task we want it to solve, and the model is able to figure this out, learn just from that input, and give us the result that we're looking for. GPT-3 is a very well-known model. One of the things that made GPT-3 stand out is its ability to handle in-context learning very well. And with GPT-3, you do what's called prompt engineering. You write to the model whatever it is that you want it to do, and the model figures it out and is able to respond and handle that request. and delivering consistently good results on quite a few tasks. So now that we have a good understanding of what foundation models are, let's get into the important point is, what will we gain by leveraging foundation models? What can each of you here gain if you decide to leverage foundation models in your job? And there are three main points to touch on. The first one is foundation model allows us to increase AI development speed substantially. When we use foundation models, there is no need to curate a large data set, no need to train a large model, no need to set up and maintain large-scale infrastructure for training. It allows our machine learning team to focus on the business problem at hand, experiment, and move very, very quickly. Second, we save a lot of money. With foundation model, we don't need to build and train the really backbone of our AI system. We save time, and we also save a lot of money on compute, because GPUs are expensive. And lastly, and maybe most importantly, foundation model provides an opportunity for all of us to tap into state-of-the-art AI with much lower cost and time. The access to state-of-the-art AI used to be fairly reserved for the large AI labs and the large tech companies. But with foundation models, the playing field is leveled. Now everyone can access state-of-the-art AI and apply it. It gives the smaller companies a leg up, which is an incredible opportunity for everyone. Now, it's important to recognize that there's also risks involved that need to be considered and managed when you rely on foundation model as the backbone of your AI system. First and foremost, bias. Any biases inherent in the foundation models will be propagating downstream for your specific application. So you want to ensure you test your system for bias and you are able to mitigate the bias. Second, as we've seen before, the complexity of foundation model is already very high and is still increasing. So this may have implications on things like downstream usage of the model, for things like serving when it's a very large model. You want to make sure you're considering this and you're able to manage that risk. Third, the high cost of designing and training these models makes some companies keep the models closed source. And this is a new trend we've been seeing. GPT-3 is a model I mentioned multiple times this talk, and GPT-3 is actually a closed source model. If you want to see the training code for GPT-3, you cannot. If you want to access the parameters for GPT-3, you cannot. You can only access GPT-3 as a cloud API. And that's something that can be okay, but that you need to be aware of and ensure that you understand what it means and ensure you have alternatives. And lastly, as foundation models become closed source, they are also starting to be abstracted and available as cloud APIs. Now, this means that relying on cloud-based foundation models make that cost you have for your downstream task go up with the usage of your AI downstream application. Again, it may be okay, but it's something to consider. Now, to wrap things up, I'd like to offer some practical recommendations for all of you on how to leverage foundation models in a smart way. The first thing is seek to leverage foundation models where possible, especially if you want to do fast exploration of AI-powered use cases. Second, understand and manage your cost factors, especially as your usage of foundation model is going to scale up. Third, understand and manage the limitation of the foundational model you rely on. Identify the bias and actively mitigate and address that bias. And lastly, follow the announcements coming out of the major AI labs. These are the labs where a lot of the advancement and new foundation models are being built and researched and shipped. And if you stay tuned to that, it will allow you to move fast within your own organization and leverage state-of-the-art AI for your business use case. Okay, so we're at the end of the session. I wanted to thank you all for sticking around, and I hope I got you just a bit curious about state-of-the-art deep learning and foundation models more specifically, and the potential it has for you to further advance AI in your own enterprise and in your own line of work. Thank you.